Right, so maybe we can start.
Yes.
Before I introduce Tom, I have to apologize to all of you. I invited Tom to speak on the 23rd today. And when I wrote the announcement, I wrote it as being on the 16th. So I'm sorry for that. And so, yes, last week it was my fault, only my fault. Sorry for that. So today it's a great pleasure to have Tom Mountford from EPFL, Lausanne. And he will speak about greedy cleaning of Poissonian dust on the French railway. Thank you, Tom.
Okay, it's a great pleasure to be able to to talk on my work. Thank you very much. So the talk, first I'll have to explain what the title words mean, but this is joint work with Sergey Foss and Takis Konstantopoulous. Okay. So the talk is just relies on basic properties of Poisson processes. It's sort of antipodal to log-Sobolev inequalities and SLEs and stuff like this. This is just very basic probability, but I hope the model is a bit interesting. Okay, so I'd like to mostly talk about the model and the background, because the background to the subject of greedy cleaners, is that there's a lot of interesting things there. Whether our talk, what we've done belongs there is another matter. Okay, so what do we have? Well, the basic idea for greedy cleaning is this is introduced by Sergey Foss and Gunther Last. But the basic idea is you have a metric space, usually, in some sense, a nice one, and you put down you have a Poisson process on this nice metric space with an appropriate measure, and you fix an initial point x0 and there is a worker or a cleaner. It's the same thing. Okay, and the idea is, well, in its original part, you have the cleaner will start at x0, then at time 1, they will move to the closest dust particle. The Poisson process should be such that there will be just a unique closest particle. He or she will clean, meaning remove the dust particle, and from this new position, they will then move at time 2 to a second, to the closest dust particle to their current position, and so on and so on. You move around, always following guided by the closest dust particle. Okay. If you have multiple cleaners, then, well, multiple cleaners, they could have share the same closest point. So if we have multiple cleaners, then what we want to do is we want to have each cleaner has an associated rate1 Poisson process, plus Poisson clock, and at the times of the Poisson clocks, they move. So they move to the nearest available dust particle, which they then remove. And they stay there, they stay at their new position for an exponential amount of time, and then they move again. Okay, so this is reasonably simple dynamics. And, well, there are many, many questions. Our question is a little bit new, but the traditional classic questions that were asked were just, if you have a Poisson process on a space with infinitely many particles, is the cleaner or the cleaners, are they going to remove all the dust particles? Will everything get vacuumed up? And when M is R, and you just have a Poisson process of dust particles, it's very easy to see the answer is no. But when M is R in any higher dimension, it seems pretty hard to know what to do. So I'd just like to sketch very briefly the idea. If it's in one dimension, it's pretty easy. You start off here at the origin, and then you have these dust particles. So what you do is you go here, first of all, I'm going to go here, because this is the closest dust particle. Then from here, this guy just beats out this guy, so I'm going to go here, and then I'm going to go here. And now this particle is the closest, so I'm going to go here. And this, just on this little move, we see quite naturally, I'm going to choose a direction. And basically, after I've made n moves, after I've made n moves, I'll be somewhere. And if I look where I am versus, let's suppose I've just moved to the left, and I look to the, so this is the leftmost point here that I visited. What you have here then are going to be, so to speak, just a Poisson process of points. Here, this distance after n moves is going to be of order n, outside of exponentially large, outside of exponentially small probability. So the chance that this guy here beats this guy is going to be, well, of order e to the minus 1 minus e to the minus cn. So just Borel-Cantelli, after a bit, you're going to stop switching direction, and you're just going to move off in one direction. Okay, so this is soft and easy. I said Poisson processes. This is very, very stable. What we're talking about is the law of large numbers. So if I, replaced these Poisson processes by renewal processes, nothing much would change, provided you had reasonable ergodicity properties. Everything that would be fine. In fact, it's if you have the exponential, on the other hand, Katja Gribich showed if you don't say where you're moving, because that's going to disturb things. You just look at the direction of your movement. So here I go to the left, then I go to the right, 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 and then left again. I'm not saying where I'm moving to, I'm just telling you where I moved. It turns out that this will be probability a half here, then probability 1 minus squared to change direction. Then it would be 1 minus 1 over 2 to the 3 to move here, 1 minus 2 to the 4 to move here, and then 1 over 2 to the 5 to change direction. Okay, and that's just because of the usual properties of exponential random variables. Okay, so it's nice result. Now, if you look at R2, or let's just say, so you have this cloud, well, points, and you move, let's say to here, then to here, and so forth. Well, it's actually very, very difficult. We don't know whether everything gets eaten. We don't know if it's, if you could call it, what the behavior of your walk is. People, some clever people have worked on this, and there have been a lot of simulations, and even the simulations aren't clear. We don't know whether everything gets eaten or not. Okay, I imagine if you're in R to the 19 or whatever dimension Remco has currently moved things down to, that you could do a kind of cluster analysis kind of argument to say that you become a Brownian motion if you have high enough dimensions. But yeah, this is actually a really hard question. So if somebody could make a contribution, that would be great. Okay. So just to say one more thing. So here I've dealt with this, but an interesting variant, which was done by people in this neighborhood, by Sidorevicius and Leo Roller, was things change if you have this variant. Now you have a Poisson process of points, just as before, a Poisson process of points starting at you start at the origin, but at each point you have, with a certain probability, it doesn't matter which, as long as all the probabilities are strictly positive, with a certain probability you have you have two particles, and with a certain probability you have one particle. Okay, and the rule is, well, if I move to something that has two particles, what I do is I clean one of the particles. Then, of course, you might interpret the rule to say, well, then you have to clean the second one. But no, that would obviously be very boring. That wouldn't change anything. What happens is if you've moved to a place where there are two dust particles, you clean the first. Then the next time you have to go away. Okay, you have to go away, and then after you've moved away, you can come back and clean the second particle. Okay, but in this case, what happens is, in this case, yes, they proved that you can have two particles. You can, in this case, no matter what the probabilities are, as long as everything is strictly positive, you will eat all the particles. And the idea is just you move along. So it's a sort of argument by contradiction, but if you don't eat all the particles, you leave particles. But that means you must leave a trail of twos behind you. And now, for the same reason, if you're leaving a trail of twos behind you, of second particles which aren't eaten behind you because you're moving off, let's say, to the right, well, you're leaving, you argue you're leaving a real density. Essentially, it's not exactly a perfectly translation invariant system, but you can argue it's more or less like that, they argue. And so at a certain point, you're going to come up on a big gap, you're going to turn around and you're going to follow and eat all the twos. You have to eat all the twos until you move to a new territory. Just for the same reason that in d equals 1, you follow off, you move in one direction. It gets increasingly hard to change direction. So this was a very nice result. Another thing I would say, another thing that I would like to mention in the background are the dynamic results considered by Foss, Roller, and Siderovicius, and Roller and Siderovicius. Here, in our model that we're treating today, you just have one Poisson process of dust particles. That's it. Okay, but another model would be you have, let's say, maybe initially a Poisson process of dust particles, but in addition, you have particles, you have arrivals of new dust particles, and your worker is going to move with a certain velocity, v. Okay, they're going to move with a certain velocity, v. So if they move, if they move from here to here, in the time they've moved from here to here, a new particle could have arrived and they move back. Okay, so you have this, but they were able to show that if you consider the process on the line, then what happens is you move to the right just as before, but you move, I think it's xt divided by log t converges to 1 or converges to a constant. Okay, you have that. And then Siderovicius, Vladis, and Leo looked at the process on the line, and they established there was a conjecture that if you move, you have a velocity as you move to particles, but if the service, you also have a service time to get rid of the particles. If the service time was less than the arrival time on the circle, then your system was stable. Your system is stable. And the reason it was a conjecture for a long time, but here the velocity doesn't matter, because if you're blowing up, you're going to have lots of particles around you, and the time to get to the nearest particle, traveling and wasted time, will be negligible. So ultimately, you have this stability here. Okay, so now I'd like to talk about our model, the model we're going to consider. So for this, we have multiple cleaners, and we have our metric space is just n half lines which are connected, let's say in R2. R2 doesn't matter. R3, it doesn't matter. We have in some Euclidean space n half lines which connected at the origin. Okay, like this. Now, in this graph distance, the distance from here to here is not Euclidean. It's the graph distance, meaning the distance from here to here is going to here and then to here. It's this distance here, okay? But we have, let's say we have n half lines where n is large. We're going to let n go to infinity. And we have n to the alpha cleaners, okay, which are initially where alpha is strictly between 0 and 1, okay? And so the cleaners are going to move. They move at different times. When their clock goes off, they move to the nearest available point, dust particle that's still available, and they move there instantly. Okay. And so for us, it's quite soft. If you have any number of half lines, could be 1, could be 2, could be infinitely many, and you have a finite number of servers, then just as in one dimension, which to repeat is pretty simple and well understood, it must be the case that every cleaner must eventually choose, so to speak, one half line and go off to infinity on the half line. Each cleaner will, it's a very soft result, doesn't matter. Here I've chosen, we have the number of cleaners compared to the number of half lines is small, but that doesn't matter. No matter how many cleaners and lines you have, every cleaner must eventually choose a half line to go off to infinity on, okay? For the same reason as the analysis of the cleaner model on R was so simple, okay? So we want to just look at and say, when is it the case that every single, or all that no two cleaners move off to infinity on the same half line? That was our question. When is it that, or when can you have that it's possible that a random pair will move off to infinity on the same half line? Now, here we have our result is just if alpha is greater than 2/3, then you will have a line, there will be random occurrences. There'll be random lines along which one or more servers, cleaners, disappear to infinity along. Whereas if alpha is small, then this isn't so. Now, I would say that there isn't really, in this case, a simple monotonicity argument that I can see why the probability of A2 should increase as the number of servers increases with capital N fixed. I haven't found a result, nor have my co-workers, but nonetheless, I think intuitively you would expect something like this. So the result is what we're really talking about, what we want to show is this is actually reasonably simple and easy to tackle. Okay. A generalization, of course, we ask, if 2 can go, is it possible to look at, is it possible for there to be M workers that disappear on the same half line? Okay, that's just a natural generalization, and we have a result in the same way. Okay, this is just so this generalizes very, very naturally, and I won't really talk too much about this generalization. I'll just say that its results are I mean, the same ideas lead us there. Okay, so just to talk about the basic properties, it's just simply all we do is for this model is we have Poisson processes, and we have extremely good regularity, law of large numbers properties, and this will help us a lot. So we also have that if you're thinking about, let's say, if you think of the number of half lines with the property that you have x here, y here, then the probability that if you look at the number of if you look at the number of half lines with the property, for instance, that the first point occurs in the interval xy in terms of distance from the origin, and then, well, actually, just this would be e to the minus x, and then it would be 1 minus e to the minus y minus x, I think. Anyway, something like this. That with the probability. But what we can say is, if x is really, really small, so this is more or less 1, we can rub this out. This becomes more or less just Poisson ny minus x, which is going to help us. Something, a simple property like this. Also, if we look at each half line and we look at the number of particles, dust particles, let's say distance 2, shall we say, from the origin, we look there at the number of these particles, then, well, the probability that you have log n particles on the in a Poisson process before time 2 is smaller than 1 over n. Is small compared to 1 over n, so that means that we can assume our environment, the dust particle environment, is good, so we have things like this. I mean, that's just a for instance, because we are going to be talking about we'll be using lots of properties like this, simple, very simple, basic regularity properties. Okay. Okay, so from this, we're going to look at a simple building block, which is, we consider a simpler model, a simple model on the line, and basically we consider R1, and we're going to consider the chance that if you start off with on a half line with a dust particle at 0, your worker is, shall we say, at x, and there's nothing here, but you have dust particles, which according to a Poisson process here, then you can ask for this, you can ask, what is the probability starting with the cleaner at x, that the dust particle at the origin is never cleaned. Okay? You can ask yourself, what is this probability? Okay, so this is never cleaned. Then it turns out that we have this probability here. We have this 1 over 2 log x, but it turns out this probability, in a crude sense, this probability, let's call it P1x, this is like e to the minus log base 2x squared, log x squared over 2 log 2. Okay, in a crude sense. Okay, and this is something we use quite a lot. And the idea for this, it's not difficult. There's nothing difficult about going on here. All we have to say is just, I start at x. Okay, this is obviously not rigorous, but it's a physics argument. But you can say to yourself, if I start off at x and x is really, really small, I shouldn't expect a particle anywhere near me. Typically, if you have a Poisson process, the next particle, the next dust particle should be of order 1 away. If x is small, that means your first move should be to the origin. You only move to x if you only move if there's a dust particle in the interval x to 2x. You only move to the right, rather. Okay? And in fact, what we say is, if you have a sequence, then you can just simply say, we want it to be the case that for every single y greater than x, we have greater than or equal to x, we have every interval y to 2y contains a particle. Okay. Now, effectively, if you look at that, well, I said every interval requires a dust particle, but really we just have to escape to order 1. After we escape to order 1 or order 1, things take care of themselves. Okay, so essentially, and this is very heuristic, but you can say, well, I want a particle at 2x, so that's going to have probability of order x. Then I want a particle at 4x, distance is 2x, so that's going to have probability 2x, 4x, and so on, all the way to 2 to the kx. I want a particle at 2 to the kx, where 2 to the kx is of order 1, or in other words, k is log to the base 2x. Okay, so if you do this, if you look at this, then, well, the probability of this is x to the k times 2 to the power 1 plus k squared, k over k plus 1 over 2, which is k squared over 2 if you're not fussy. Okay, but this is going to be, therefore, x to the k is 2 to the log 2x squared, 2 to the k squared over k, and this is minus, and this is going to be log 2x squared. So you look at this and you get the result like this. Okay, now that was obviously, in some sense, this argument is nonsense, because the probability that you have something at 2x is 0, of course. Okay, but what I want to say is, what makes this work, the simple argument, is instead of saying I have something at distance at x, I have a particle at 2x, you can say I have a particle at distance in the interval, 2 minus x to 2x. And then from this particle, wherever you are, you can say I have so you have an x1 in here. And then you have an x2 in 2 minus epsilon x2 to 2x2, and so on and so on and so on and so on. The same calculation goes, except that we don't have log 2. Essentially, we have something like log 2 minus epsilon, but that doesn't matter. And you have an epsilon. So the probabilities would be x epsilon, essentially 2 or 2 minus epsilon, but it would be 2x epsilon, 4 epsilon, and so forth and so forth. You multiply these together, but this gives you a factor, epsilon to the k, whereas the real factor is e to the minus k squared over 2 log 2 log x squared k squared, sorry, where k is log 2x. Sorry, I'm not sure this constant is right. Sorry, you have an epsilon to the k, e to the minus k squared. But the point is, this epsilon to the k, if epsilon is fixed and e and x is going down to 0, this is going to kill this. And so you have the probability satisfies this. You have this result, okay, which is going to be useful to us. Okay, and this generalizes perfectly well. You have the same ideas, but this is would lead us to talking about M particles. If you have M servers, which start off pretty much the same, you just want x1 up to xm to be more or less around x, around some value x, then you have the same value, or the only price is you just have an M, which is fine. Okay, so you so we understand these are what we call escape probabilities. We have these escape probabilities. Okay, so now when analyzing our motion, when we analyze our motion, we have a cleaner moves after. If you forget about the first move, which is from the origin, a cleaner is going to move. When a cleaner moves, they will be out on a half line. When they move, they either move up the half line further away from the origin, or they move to a new half line. If they move to a new half line, we say they skip. Okay. Now, most moves should be skips, because the first initial moves you make, you're moving to something close to the origin. Beyond this close to the origin point, things should be a Poisson process. The next distance should be of order 1. So if you've moved to x, you should basically, there should be some other close point on another half line, something of order x, distance x away. So the total distance would be 2x, and so the probability of moving, of skipping, should be very close. Okay, so what we found very useful in analyzing things was we introduced the idea of looking at times when we skip to a particle of distance x away from the origin. Okay, this will turn out, this is sort of a good index for our process. Okay, we also can look at the distance of the closest dust particle to the origin. If you're following the movement of the workers, you know whether sigma x has occurred by a certain time. You don't know what rho t is at time t. Okay, so another result is the following. Suppose we have, if we skip to a dust particle on a line, this is just notation for a line, some line. If we skip to a particle, so we have a half line, we're here, a server is here, and they skip to a new point, x, here. This is the origin. And this distance is, if you're not too fussy, if you just look at it in this sense here, we have this distance x is of the order e to the minus k square root of log n. Then in that case, we could have lots of other particles, workers, on the same point. Okay, but nonetheless, if we just looked at this and we went back and we said, well, this is e to the minus k square root of log n, so log of x, of course, is minus k square root of log n. So log x squared is minus k squared log n. So e to the minus log x squared over 2 log e to the minus log x squared over 2 log 2 would be like would be essentially like this. If you forgot about these guys here, then this would be your probability of escaping, approximately. Okay, now it's quite technical, because actually what we're doing, I don't want you to digest all of this because this is quite technical, but what we do is we We don't ask that you survive, because that's complicated. We ask that you survive up until the first skip to a particle of distance 1 away from the origin. That's what we ask for. Then what we have is, you have a reasonable chance of just moving off to infinity, well, reasonable in terms of this probability here. And you have, and then there's this factor 1 over log n plus 1 squared. Why is that? Well, basically, you have these competitors here. First of all, you've moved to x. That means that the closest particle to the origin when you skipped was x. This closest particle, the distance, shouldn't move too much. So in reasonable time, you have a reasonable chance of moving to something like 3x over 2, and then you might have a particle, let's say 5x over 2. You might have dust particles here. The price of this is very small compared to this probability here. So if you have this, you want to say who moves. It could be one of these workers, or it could be this guy. But the number of workers on this half line can only be at most log n. So what you want to say is the chance this guy moves before these guys do, this clock move, the clock for this worker moves and you move to here, is going to be of order 1 over log n. So the chance this happens twice is going to be of order log n squared. After this, you have a reasonable chance of just escaping, escaping and leaving these guys. So we have this chance. Every time you move, you skip to a new line where your distance, basically e to the minus k square root of log n away. You have this probability of escaping. So what we can actually see, here is that if you look at this C here, what we have is you will make skips for any epsilon whatsoever. You will make skips to a distance for any epsilon, you will make a skip to something which is of order e to the minus c plus epsilon square root of log n, where c is this constant here. And what that means is, well, what happens is you have many half lines, but after a bit, you have many half lines, but once the closest particle to the origin gets close to this guy here, this probability here of escaping gets to be like 1 over n to the 1 minus alpha. And 1 over n to the 1 minus alpha is about the time it takes to change the size of to change materially the size of the particle that's closest to the origin. So what happens is, up until some time like this, most particles, some rare particles may escape, but most particles, when they move to a new half line, they then return, they skip. But what we have is there comes an explosion at this stopping time. What have I done? There comes an explosion at this stopping time. And so we never actually reach this guy here. We never reach this rate because applying this lemma, most of our particles will escape to, all of our particles, in fact, will escape to infinity before we can clear out this number of particles. So our result then comes from the following consideration. Up until sigma e to the minus r constant plus some epsilon square root of log n, up until the closest particles increase to this amount, almost all particles are going to be skip, are going to return and pass through the origin. They're going to skip. Now, as you move from e to the minus c plus epsilon square root of log n to a closest part e to the minus c plus, let's say, epsilon over 2 square root of log n. Of course, square root, if e to the minus anything square root of log n is smaller than any power. So so basically n times this is really of order n. If you look at this now, if you look at all the Poisson particles, you look at where the distances, you have a rate n Poisson process. You have a rate n Poisson process, and you have a rate n Poisson process if you're not fussy about about corrections like this, and so for this to change from here to here, we require of order n particles to be removed. We have n alpha guys. So the time will be n alpha times n to the 1 minus alpha, which will be of order, which will give us n of order n moves. Now, each move, when you move to a particle, when you move to a new edge, you want to say what is the chance someone else can move to a new half line. You want to ask yourself, what is the chance somebody can move to this half line after you move to this half line, and you can escape together? And the heuristic is, the probability of that is, well, the best way to do it is if there's a particle here which is within distance n to the minus 1 minus alpha. And this has to do with the fact that if you're closer than this, if you're closer than this, then some particle can move before this guy moves, or anything moves here. But if you're farther away from this, then you can say that by the time this guy moves, nothing will have moved to this guy. So the probability that these two guys escape is the probability that you have a dust particle very close to where you moved, and then times the probability you escape, which is going to be n to the minus 2, 1 minus alpha. That's the chance for one move. But we have, by this heuristic here, we have of order n chances, n moves that happen. So you look at this and you say, this is n, this is times this, that's n to the 3 alpha minus 2. If alpha is greater than 2/3, this goes to infinity, which is another way of saying you're very likely that one of these things happens. If alpha is less than 2/3, this goes to 0, and your chance of escaping of having a double escape is very small. So that gives us our result, which I'll just flip back to. So we have this result here, and the same argument generalizes very easily to n. So I'll stop sharing for the moment. That is the talk. Hello?
Can you hear me?
Now I can, yes.
Okay, great. So are there questions?
So as I say, the probability part is really quite basic, but what we thought was it was an attractive model, and maybe somebody has something to say. Maybe somebody can recognize this model in other things.
So questions?
I have a comment.
Yeah.
Question.
Yes.
Go ahead, Pablo.
Okay. So thank you very much, Tom. Very nice talk. I haven't thought about this problem. So I thinking about instead of playing with the number of lines,
Yes.
you could play with the density of points, like put 1 over the distance to the origin, for instance.
Yeah.
So you have,
Yes.
you have that, and you allow also to go with the Euclidean distance.
Euclidean, okay, Euclidean distance you can certainly do, but if you do Euclidean distance, then you have to specify. I mean, I imagine that the neutral choice would be the n particles are uniformly spaced, let's say in R2.
Your density is 1 over the distance, then you can jump from one line to the other.
Right, but then all I'm saying is to fully specify the model, you want to say it depends on the angle between the n half lines. If they're all scrunched together, that's a different model.
Of course, yes.
Yeah.
Yes. Well, there are some parameters that you can play with.
Yeah.
So yeah, I
But
think that maybe because this model, in some sense, would mimic more the two-dimensional problem, I guess.
Right. I would say, yeah. I mean, but again, it doesn't have to be in 2 dimensions either. You know, you could have.
Yeah, of course. But you could do it in 3 dimensions, but then, yeah. Also, you can do in any dimension, in fact.
But I suspect, okay, my action is ultimately you're going to get the same type of results if you have the Euclidean distance as well, because ultimately things that as you move away. But
no, because your density is very low. Then it's 1 over the distance to the origin.
No. Right. No. Sorry, I was saying right. Sorry, I thought there were two models. One is the Euclidean distance. One is if the density goes down. I think
both together.
Well, I would say even if you stick with my original model, but you have the density going down, you're going to have qualitatively different behavior.
Yes, of course. Yeah.
I believe that would be interesting to look at. Yeah, I haven't thought about that. I think Katja in her thesis did something along with playing with the densities, but I don't think it's relevant to the problem you suggest. Okay. But I think if you just keep it, everything is a Poisson rate, whatever, rate 1, then I think Euclidean distance is not going to change the results, qualitatively change the result.
No, I agree.
Don't believe, but I think I think playing around with the density will definitely make things interesting. Yes.
Okay.
Yes.
Thank you, Tom. Thank you for the talk. Very nice.
So.
Yes, I was wondering if you looked at the problem of how many cleaners you need to clean the whole system. So I guess
right. You have a large.
It has to be more than n because there's
right. And that's about all I can say right now. Yeah. We have thought about this. Absolutely. Yeah. So right. It's sort of it's just a question of there is a sort of large deviation. I mean, well, I don't want to say hydrodynamic limit in Claudio's presence. I don't dare say that, but you have a law of large numbers if you have a large number of servers, you're going to have you're going to have a law of large numbers. You're going to have a sort of interplay because you could have some half lines which don't have many people from of order log n. Don't have are empty for the first log n, shall we say? And maybe this means that everybody moves. You could have everybody moving up on the half lines and then ignoring these, perhaps. So, I mean, you have things like this. One point I would make is what you have when you have many more servers is on one particular half line, you're going to have teams of server that work together, like in the Tour de France, the peloton. And the point is, they're going to the more people are in the team, the quicker it's going to move, because you have effects like this. So yeah, we've thought about it, but we haven't made much progress.
Okay, so if you have I don't know n to the 1000, you're not able to say that that all the lines will be cleaned. Even if you take a huge number of servers.
Yeah, I'm not sure. No, I don't.
No,
I don't know how to deal with it. I don't know how to deal with that. But I mean, that doesn't mean it's not simple. But it just means I don't know. I've thought about it, and I don't know how to do this. Yes,
it makes it more interesting. Thank you.
Yeah. Oh, I agree completely.
So also I have a question. Tom, thanks for the talk. I was wondering if, okay, so you are looking at asymptotic events. So if you could find timescales in which, if you look at these timescales, you will observe different qualitative behavior of your model. See, because
when we say the model, you're referring to still having a whole bunch of half lines.
Yes, exactly. So you have n half lines and alpha cleaners, and instead of looking at t to infinity, you look at time n to some power, and then and the number of say lines in which you have cleaners, or the positions of these cleaners.
The great majority of lines are just untouched. They're just not touched because everything disappears. There's this critical value, this critical distance. I mean, understood in a crude sense, this critical distance, e to the minus k square root of log n. And obviously, most half lines don't have any particle in that distance. They're all of order 1. But all the action occurs up to time n to the 1 minus alpha times some corrective value. That's when things happen. Beyond that point, mostly you have just, well, of order n to the 1 minus alpha, I think it is. I'm not swearing to this. You have this number of half lines which are used and the rest aren't used, and you're going off to, and by this time, well, by this time, most of the particles are a good distance away. Will be a distance away. Yeah, I think, yeah, no, I mean, I think what you're asking for requires a finer analysis than we have, because for us, we kind of avoid things like this. For us, in our analysis, n to the 1 minus alpha is the same as n to the 1 minus alpha plus epsilon, or something like this. You know, I mean, for the purposes of our result, we can say things like that. Whereas for your question, I don't think you can. I think you're going to have to really tie things down. So I think it would require a more ambitious analysis. If you go to our little proofs, of the P1X, you know, our result is quite crude, and that's perfectly adequate for our purposes. So we'd have to get a bit better than that. But I don't think, you know, what's going on is not mysterious in calculating P1X, the probability starting at X that you never reach the origin, you never clean the origin when X is really small. It's not mysterious. So I think we could do that. We could do something, but but whether we could arrive at what you're asking for, I'm not sure.
Thanks. Any other question?
Yeah, you have maybe a comment, I mean,
Sure.
about like some possible modification of the model that makes it maybe more stochastic, but maybe easier to study, is what if you replace this rule that the cleaner, they move to the next, like the closest particle,
Yes.
to something with a dispersal kernel, where you are more likely to go to the closest, but you can still go to the second closest, the first closest, and so on. And so that makes it more stochastic, but it seems that it might be easier to study. I don't know.
I know my reaction is it would be harder, but
You think it would be harder?
I think it might be harder, yeah. But I think, okay, the dispersal, when you're saying the dispersal, do you want, I mean, to me, what I would like when you say I want dispersal is there's not one privileged element. You're choosing essentially from a large number of guys. You could, given your environment. So would that, then this dispersal, maybe you'd want this dispersal to be a function of your distance from the origin, perhaps.
Yeah, I mean, something like you move to the closest particle with probability 1/2 to the second closest with particle 1/4 to the third closest with particle 1/8, something like that. And so that means that you can have access to more, you know, particles. And so eventually you may have a theorem that says, yeah, if you have enough cleaners, then they can indeed clean everything. Or you don't block access. You don't block access to anything, in fact.
I'm sorry, I misunderstood. You're talking about Hubert's suggestion. I misunderstood. Yes, I absolutely.
Okay.
Yes. Now I understand. Yes, that's for that problem. Yes, that would maybe that's worth thinking about. Yes, but I think also there may be. I just haven't thought hard enough about it, but I think, but yeah, that's a good. Right. Yes, I believe that. Yes, right. That makes sense. Yes. For the reasons you say. Yes. Thank you.
Yeah. No problem.
So there is a question on the chat.
Okay.
So can you see from Alberto? Can you comment about the?
So you have, so you're saying, so you have, I mean, the rates don't really matter, but you have a Poisson process on R, and then you have a Poisson process of cleaners. Oh, a Poisson process. So is the question that you have then a Poisson process of dust particles and a Poisson process of cleaners? Or is that, so, I don't know. To me, my guess would be just everything gets killed in of order 1. I mean, everything just, you know, it doesn't matter about the rates. Ultimately, everything is going to, I mean, I would say it would get, you would very efficiently grow, and everything, you would have to, I would suggest by time n, you would have to go distance exponential n from the origin to find a dust particle, or something like this. I would suggest, because it would be carnage. I mean, it would also be reinforcing, because if I'm moving to the right, I'm going to come up against something that's moving to the left and killing lots of particles this way. So I would think it would be quite efficient in killing, getting rid of the dust particles. So I haven't thought about it, and I do think that you can say something interesting there. Yes, I think there's an interesting question there. But my instinct is to ask where, after time n, where I would turn it into a where is the closest dust particle that still exists. But is that? Do you have some other question in mind?
Alberto?
Oh, sorry, Alberto.
No, okay.
Okay, but thank you.
Any other question? Well, if not, let's thank Tom again. Thank you, Tom.
Thank you. It's always great, one way or another, to be in Brazil.
And we continue so next Wednesday. See you in a week. Bye.
Yeah. Okay. Yeah. Thank you very much. Good luck tomorrow, but not on Monday, I think it is. Bye-bye.
Bye.